Hello, y'all. Darrell Weber Jr. back with some problem solving, thermodynamics. So basically, we're continuing from where we were earlier. I didn't fix the live chat. Let me fix the live chat really fast. Be sure to drop a line when you arrive. If you have any questions. Right, see that chat now. Now go to the shared screen. See why the stream failed. And y'all are welcome to join Discord if anybody's there wants to ask questions live. Boom, all set. So we'll be doing problems 16, 6, 17, and 18. Let's see how those go. All right. So we have the most common measure of the fluctuations of a set of numbers away from the average is the standard deviation, defined as follows. Right. Standard deviation is usually written like this, if I remember right. And if we square it, that's called the variance, if I remember correctly. Let me know if I'm incorrect. The most common measure of fluctuations of a set of numbers away from the average is the standard deviation, defined as follows. For each atom, the 5-atom toy model of figure 6.5. Let's go to figure 6.5. Right. So we have E going up, have all right, so that's the figure we're working with. Compute the deviation of the energy from the average energy, that is E minus average energy, I 1 through 5. All these deviations change in EI. Right. So it's saying deviation. I don't really know the symbol for deviation, if there is one. I would just say the deviation is defined as delta. So we'll say delta equals the energy of the state minus the average energy total. So if we were to do delta, we also call this 1, 2, and 3. Delta 1 equals E1 minus the average. So E1 equals 0 electron volts. And we know how to compute the average from earlier. This should be the probability of 1 times the energy 1. And let me make sure I wrote that properly. Yep. And I have to actually add them all up. Hold up. I, technically, this will be probability I, energy I for each of these. So let's take a look and see what this is. Well, we actually did it earlier, but I'll do it again for practice. So the average energy equals 1/5. That's a probability of 7 electron volts plus 2/5. It's probability of 4 electron volts and 2/5. That's the probability of 0 electron volts. So that equals 7 plus 8 plus 0 divided by 5. 15 divided by 5. So that's 3 electron volts, which is what we had before. And deviation of 1 is going to be E1 minus the average energy is going to be 0 electron volts minus 3 electron volts. So the deviation is negative 3 electron volts. The deviation of 2 is the energy of 2 minus the average energy. So that is 4 electron volts minus 3. So that's 1 electron volt. I'm not sure of this. I mean, it doesn't say it needs to be positive or negative. I mean, I wonder if I need to make this like the absolute value. It doesn't say that. So I'm supposed to be doing 17. Oh, well, it says I1 through I5, but there's just 2.2s. I guess I can do 2A. That's going to be the same thing as 2B. So maybe they have something in mind later. And the deviation of E3 minus equals 7 electron volts minus 3 electron volts. So that's 4 electron volts. And we have the same thing for the last state. Right? So that seems easy enough. All these deviations change in EI. Oh, well. So I guess they did give us a symbol. I just have to read a little bit farther. All right, so we have that. Compute the average of the squares of the 5 deviations. That is square E. To compute the square root of this quantity, where the root means square deviation or standard deviation. Call this number sigma E. Does sigma E give a reasonable measure of how far the individual values tend to stray from the average? All right, let's try this. So changing E1 squared equals 9 electron volt squared. Changing E2A squared equals changing E3A squared equals 1 electron volt squared, and changing E3A squared equals changing E3B squared equals 16 electron volts squared. All right, it seems good. So we know that the expected value of x is going to be the sum of the probability of I and the value of x at I using the equation from earlier, that one there. I wonder why. Okay, we don't actually have to use the Boltzmann factor because we can see the probability clearly, but when it becomes more complicated, so I was just thinking, well, I could discretely see the probability. I don't imagine they want us to use the actual Boltzmann factor. Let's look at, yeah, for this example, for that figure that they use the explicit probabilities. So, I mean, I imagine you're going to get the same thing if we use the Boltzmann factors. It's going to be more complicated. You have the same exponential, but the uh, exponent will be changed accordingly. I don't think I want to try to find out. And be sure to drop a line if you have any questions, those who are viewing, or any comments, let me know. I believe the chat is working fine. All right, so let me add another page here. So, the average of, should write EI, I'll write it the same way they have it in the problem. It's a bit too far. So x equals change in EI. So change in EI, average value of that is the sum I, probability I, and the value of change in EI. So that'll be 1/5, 9 electron volts squared plus 2/5, 1 electron volt squared plus 2/5, 16 electron volts squared. That equals, let me square this here. I think that seems right as far as my notation. So I'm real big about notation. It helps me understand it. All right. So we have 9 plus 1 plus 16 electron volts squared over 5. So that's what? Is that 26? That seems to be right. All right. So this must be the variance I was talking about here. If I'm thinking about that correctly. I could be remembering that incorrectly. What's going on, Galva? I forgot to multiply the quantities. Hold up. Put them right here. Oh, crap. Thanks. I did. There we go. So we have, what, 34, 45. That makes more sense. I was wondering why it wasn't a round number. So that's 9 electron volts squared. Thanks, Galva. Appreciate it. That makes things a lot better. All right, so we have that. Mm, and it could have been just that fast when I saw this 9 times 1 and it ended up being 9. I could have just continued doing the same thing and just writing that there. Sometimes I make that mistake. If one is multiplied by something that's simple like that, I just follow the same pattern. Would have been what I did. That definitely makes a difference. All right, so we have that. Thanks again for dropping the line, Gelva. Now, the odd thing is, I'm trying to think about this in a different way because I remember from my probability class, this when I first learned about the standard deviation. Um, and we did the whole derivation, which I don't remember now. Uh, but what was it? Yeah, I believe it was that. The square root of that squared minus that squared. Just like that. Okay, okay. I'm with it now. So where did I calculate the average? I didn't do that yet. No, I did right here. So average value of E. So that we're doing a change. So the change in E is, did I get the average of the change in E already? Doesn't look like I did. I just did the square one. So let me get the average value of the change in E. So I don't remember this. I guess because I'm taking the square root of it. I guess that's what they're saying. Yes, I took the square root of the change. They compute the square root of this quantity, which is the root mean square deviation of the standard deviation. So it looks like they're saying that just the square root of this. So they're saying this is the standard deviation. And now they want us to prove, and does this stray from the average? Yeah, I guess so. I mean, 7 is exactly 3 from the average, but 0 is like 4 from, 7 is 3 from the average, 4 is 1 from the average, and 0 is 3 from the average. So I guess most of them is 3 from the average. I remember right, the average was 3. Oh, let me see if I, oh, oh crap. I must have been wanting an even number. Thanks, Gov. I appreciate it. Now I'm back with a fraction again. Mm, yeah, I was all happy. Thinking I had an even number. Let's see here. I should write it as a decimal. Well, it's not so bad. It's 8.6. Thought it was going to be worse. That's not so bad. So it's saying EI squared, the square root of that, the square root of 8.6 EV squared equals 0.93 electron volts. Which actually makes more sense as far as the deviation, I guess. So if 3 is the average, 5.93, actually not. Okay, well, as I was trying to do this, I don't even remember what type of stuff we did this with in probability, but I know we did this a lot, but it was just more like just numbers. And it's odd. And I could explain why when I'm doing physics problems, like in, um, what class was that? I think even some of problems like this as well, I try to just make it into a math problem. But I'm trying not to do that. I'm trying to actually just do the problem like problem. But I guess I could just, you know, name everything X, and it makes more sense like this. But then it's like I don't have to transfer everything around. But awesome. Thanks for another catch. All right, so we're looking at this. So I believe they're saying that's a standard deviation. That's either a reasonable measure of how far the individual values tend to stray from the average. I mean, I don't know. What do you think, Alva? Like 7 is one of the values. The average is 3. So that's only what, 5.93? 0 is 3 from it. 4 is almost added. I mean, I guess if you take into account all the values, I mean, I guess that's what they're saying. If you take into account all the values, this seems to be sort of roughly how far the individual values tend to stray from the average. All right. So now we're going to try the other part. We'll see how this works, which is how I normally remember it, that the standard deviation is the square root of the average of the property squared minus the average of the property squared. All right. So now we're not going to do the change, I imagine. So we already did the average, which was 3. So the average E equals 3 electron volts. So that average squared equals 9 electron volts squared. So that's this one. And if we square the values to get the average of that, which I don't think we've done yet. So that'll be E1 squared equals, call that 0 electron volts. E2A squared equals E2B squared equals 16 electron volts squared, if I remember right. And then we have E3 A squared equals E3 B squared equals 49 electron volts squared. Add another page here. So I'll get the average of these squares. We have the average of I squared equals the probability of I squared times the value of I squared, which is 1/5 times 0 electron volts squared plus 2/5 times 16 electron volts squared plus 2/5 times 49 electron volts squared. I wrote down the values correctly. Yep, 0.47. So we'll see if this gives us the same thing, which will be if I did this properly after I get to the last part. So I should try to multiply this time. So that's 0 EV squared plus 32 EV squared plus, I forgot what, 98 EV squared over 5. So that's what, 130 EV squared over 5. We do have a round number this time. 26 EV squared. I think that's right. I just use a calculator this time to make sure. 32 plus 98 divided by 5. Yep, 26. That's the average of that. And all right, so let's see if this adds up. So we will see if sigma E equals the square root of the average of that squared minus the average squared. Did I write that properly? Oh, I reversed it. Let me write this better. The average of the thing squared minus the average squared. It's the average of the squared thing minus the thing squared. So that'll be square root of 26 electron volts squared minus uh 9 electron volts squared. So that'll be what? 17? That doesn't seem right. Let's see. So now we're getting 4.12 electron volts. So I think I did some math wrong somewhere. Let's see what I did. Unless I'm thinking about this problem incorrectly. Let's see. Understanding is that these two should equal square, square, square. Those are those squares. Mm, mm, and the average we got was 3. That's 9. Ironically, it seems to be almost like the other side of the this one. So this seems to be right. The -3, 1, 1, 4, and 4. Well, it looks like my issue is here a little bit. Seeing what they meant by the change in E part squared. I'm going to label these sections. This is A. And these are all positive. Now the probability is correct. I believe they are, because we have the change in energy here, which is the energy of the particle minus the average, as they have it here. And that seems to be right. 0 minus 3, 4 minus 3, 4 minus 3, 1, 1. And we have one of these, two of these, and two of these. So I believe that part is right. It looks like when we get to B, I think I calculated the change, because it's actually this change in E squared, is the average of that is kind of new to me. So, okay. Oh crap. No, hold on. Did I mix up? Like I see what you mean. Maybe I mixed up which one goes where. Should it be 2/5, 2/5, and 1/5? Are you saying that right here it should be 2/5, 2/5, and 1/5? Ah, oh crap. That's what I'm doing. Yep, I think I swapped my numbers around. Thanks. That would explain it. All right. So technically this should be, what's the easiest way to swap this around? So all I have to do is make this one 3. Yep, thanks. That should stay 2. And this will be 1. So then I would have to copy this out and move this here, paste this here, and uh, 17. So then 2 of those, and there we go. Thanks for the catch. Probably because I numbered everything. No, I mean, that's how I intended to number it. I just swapped up the order a bit. Thanks for the catch. That would explain it. All right, so let's see what errors this crept in. So that means I would have one of these. I would have 2 of these, which would still be 1 electron volts. And then I would have 2 of these. All right, so that seems to be correct now. Thanks for the catch. So I still have 2 of those, and I have 1 of those. So then I have 18, 2, and 16. So now I have 38. Awesome. And this probably is going to equal the bottom one now. So the bottom one, no, actually, hold up. Didn't I switch? I guess that answer will have to change as well. I don't think I started over from the beginning with that. So 38 divided by 5 ends up being 7.6. Interestingly enough, it's close to the other value. 7. Oh, added up wrong again. Oh, thanks. Crap. 7.2 and 7.2 to square root. Let's see what this one is. And what was it before? This one is 2.68. Let's go back to see what it was before. Well, when it is different. About what? 0.3? Right, so we got that. Yeah, so I have to do these again as well because I had the values mixed around. So now that I swapped the numbers up, E1 squared 0 squared, E2 squared is now, that's still 16, E3 squared is still 49. But that seems to be the same because I didn't swap the numbers up for the original one. Probability of the squareds. So this would swap up, right? Oh yeah, so it did. So what I have to do is get this swapped up again. So this will be E1A equals E2 E1B squared equals 0. And this is just one of them now. All right. So then we have the same probabilities here swap. 2/5, 2, 1. So then we end up with that still 2. This becomes 49. And that becomes what? 81. Went over wrong over. And what's 81 divided by 5? 16.2. I mean, seems promising, I guess. So we'll see. At least I understood the general idea properly. I just mixed up the, oh, and did I catch the 36 you were talking about? Yeah, we talked about that earlier. And all right, so we have that. And that should be the expected value of the squares. All right. So this should be 16.2 minus, so that should still be the same. Square root of what? Oh, there we go. That seems familiar. 7.2. That's what we had before, right? Yep. Now it finally adds up. Oh my gosh. And I did it without making it a math problem. With some help from Velva on the algebra. All right. We have square root of 7.2. We did that earlier. 2.68. Ain't that something? We've proved that the standard deviation squared is what do they call it? The deviation, the square of the deviation. I have to think about that. This way of doing it is new to me. I can't remember exactly how we did it in uh, probability. Maybe we did do it that way, but then we focused on this formula so much after that that I forgot. And this one here is this one. Oops, hold up. Yeah, that's right. All right, well, that's cool. And so what's the last thing they want us to do? This long ass problem. That was C, I guess. A, that was B. This is C. And let's see what we're doing for D. I should look at it in the textbook. Have a look at that in a bit. Check the preceding formula for the 5-atom toy. I should have did this whole time. Check the preceding formula for the 5-atom toy model. Yeah, we just did that. What do you think, Elva? Are they saying something else that I missed? I thought we literally just did that just now with A through C. Seems like they're saying do the same thing again, but we just did it. Okay, thanks. At least that's not just me. And actually turning this in, by the way, like this is literally what I'm going to turn in for my homework. So that's one reason why I like to color code and stuff. Uh, and also so I can go back over it. So this is the new section. So like I think you might have came after the intro, Galva. So today in class, what the professor said he's going to do, like I have started reading right before class, the section here. What the professor said he's going to do is he's going to, so half of the exam is going to be questions from the previous exams. We had three. The last one was this week. I didn't do so good on. But we get to do a like a we can redo the exam to get half of the points from the problems that we missed. So when I do that, I'll have an 85. Other exams, I ended up with like an A after the redo. So this is like the worst exam I did so far. But that's for the chapters, what, 4 and 5. So I have some time to study that. But suffice it to say that for this final exam, he's going to take problems for the first three exams, but he does change the problems up a bit. But it'll be the same, generally the same problem. So he was like, if you just study the first three exams, then you will be that's half the problems down for the exam. And the second half for the exam, or the other half, will be problems from this section. So right now I'm on section 6.2 in the book. So this goes all the way uh to 6. Oh, I forgot. This is the PDF that we get access with as students. Like the school has like subscriptions to certain uh, repositories of data. So we was able to get this book. This is actually a pretty good book too. I can't show you the table of contents, but suffice it to say, this section has about 6 subsections. So it'll be on chapter 6 and the first 2 sections of chapter 7. So all of chapter 6, which is what I'm working through now, and the first 2 sections of chapter 7, that's what I'm going to have to make sure I fully understand so that I can do the exam. So another reason why I go through all the steps like this is so that I can come back and study the problems. So these are the ones I did before. I know I didn't do all of these on stream. Um, but this was the first problem. I mean, the 6.2, but the first problem we had is the basic calculations with reservoirs. This one, what article in 3 states where we're calculating the Boltzmann factor, the partition function. So that was like, I did some of these on a previous stream. This one I believe I did on my other channel as a brief overview. Like I go in more detail on this channel where I actually work through the problems and y'all can see all the mistakes I make and stuff as well. And the other one I do like sort of like an overview of stuff I did already. But we did one of those problems. And these are the ones I'll be doing in the future. So 6.18, 631, 632, 638, 641, 643, 644. Then we go to chapter 7. I have 7.2, 7.7, 7.8, 7.11, 13. So that'll be the end. So this homework is actually due next Monday. He actually allows us to work in, oh, and y'all didn't even see me scrolling, did you? I'll scroll it one more time. Sometimes I forget to switch back. But these are the ones I have. I'll go in reverse. 7, 13, 11, 8, 7, 7.2, 6.44, 4, 3, and so forth. So let's keep the numbers of, so I can know where I'm going. So that's for those. So these are due on Monday of next week. So I have plenty of time. And I need to set up a time. He lets us work in groups. And my friend Austin, who we worked really well together in our previous class, we decided to work together. So usually we get together like a week before the homework is due, which is this week. We'll probably get together Wednesday and go over our responses, see how well we did. Sometimes we actually split up the homework and he do half, I do half. I think this time, I don't know actually how he's doing. He might not have started yet. I'm not sure. But I started the first part since something what I had. So where we at? About an hour. What do you say, Java? Do you want to see 6.17? Are you ready for not 6.17, 6.18? Or are you ready for a break? Let's see what 6.18 is. Let me scroll this. All right, well, at least it's shorter. It's one thing. I think I could do this real fast. This is still from the same section. So what does it say? It says prove that for any system in equilibrium with a reservoir at temperature T, the average value of E squared is this. Hold up. Prove that for any system in equilibrium with a reservoir at temperature T, the average value of E squared is, okay. Then use this result and the results of the previous two problems to derive a formula for sigma E, or for the standard deviation, in terms of the heat capacity. Okay, now they're doing too much. You should find, and I hate proofs. I absolutely hate proofs. The good thing about it is we can pick one problem that we skip. So I haven't seen the later ones yet, but usually I end up skipping the proof problems. Or you let us skip one without a penalty. Something like proof, like you have to find some like super duper long calculation problem for me to not skip the proof problem. So my first impulse is to skip the damn proof, but since we're all here, I'll go ahead and try to go through it and see if I make some progress with it. Maybe I'll try it for like 12 minutes. See if I make some progress with it by the top of the hour. I mean, will proofs be part of the exam? Generally, no. I mean, I can't say for sure. Actually, you know what? There was a proof on the second exam. I'm pretty sure I did horribly on it. Matter of fact, let me get the exam real fast. I didn't even look at it closely. Give me a moment. Take a look and see. So, I kind of knew I was not going to do extremely well on this one. So, and I didn't even, usually I take a picture of it and put it in my file so I could like have it on my pad, but I didn't do that yet because I just got it today. And I surely did horrible on the proof. There was a proof on this exam. That's the worst problem the worst. So in other words, the problems, the you get. Oh, hold on, hit the wrong button. So the problem, it's the exams. All the problems have 4.14 points. So if you get the thing 100% right, you get 4.14. And they deduct points as you go. You know, if you get stuff wrong. So on this exam, I got a 4.14, or is that a 414? I'm sorry, yeah, it's 414, not 4.14. I'm not sure. It doesn't really matter. So I got a 4.14, I got a 2.14, a 3.14, a 2.14, and the proof was a 1.14. I don't know how everything has a 1.4 at the end, but they do. That's just how it is. So, so this is the scores I got on the 5 problems on the exam, and I ended up with a 25 out of 36. So this was my worst exam. The first one I made like an 89. The second one, no, the first one I made like a 86 or something like that. The second one I made like a 89, and I still did the redo. So when I do the redo, I'm gonna end up with like a 94 on the second one and like a, I don't know, it'll be like a low A on the first one, whatever it ends up being, or a high B. This is definitely my worst exam so far. And this was the proof. So you are correct. I might have a proof on the final. So I'm going to have to pay attention to it. Okay. So let's look at it. Thanks for that. So Galva's keeping me honest on here. I need to stop skipping the proof. It's probably why I did so bad on that proof on the exam, because I like usually skip the proofs. So the problem was basically to derive a thermodynamic identity. Oh my gosh. And but I did pay a little bit of attention to it because I went to the professor's office hours, and I did actually start that problem. Then I was going to skip it. I think that particular homework assignment, they had another problem that was so ugly that I went back to the proof. So I ended up like fumbling through it, but it was like right before the homework was due. I didn't really pay attention to it in depth. And the professor was saying you should understand that, so they made me look at it closely as well. So I kind of knew it was going to be something like it on the exam. So I have to see for the last one. So, I mean, perhaps I could meet for the final. So, I mean, I believe I could copy some of this stuff down. Um, like we know that this is the case. We know that I'm sure I wrote my expected value down somewhere, or maybe I didn't. Maybe I'm thinking about my notes from earlier. Here we go. I just wrote it in terms of x. We know that this is the case. All right. So prove that for any system in equilibrium with a reservoir at temperature T, the average value of E squared is. All right. So one thing we learned earlier was to get the energy of the system, you can get the energy of one particle. So the energy of the system, I guess they use U for that. The energy of the system is N times the energy of the particle. So I remember reading that in the book earlier. So I think this is what they're getting at. This is probably why he assigned this problem. I have so many things in my toolbar. Maybe I gotta remove some of those. So I was scrolling for something earlier. So here we go. So this is 6.19. Oh, average value. And here it's saying that for any system in equilibrium with a reservoir, the average value of E squared is that. So I assume they mean the energy of the system. So in this case, it's saying that if I'm thinking about this properly, it's saying that the average value of U squared equals 1 over Z partial squared Z over partial B squared. Yeah, I'm gonna be horrible on this one. Uh, so I know that Z, which is the partition function, is going to be the sum of what? See if I can remember this. I'm going to have an exponential B and the energy of the state. And there's something here that I can't remember was there. Let me scroll through and remind myself of what that is. No, oh, there isn't anything there. Maybe I'm thinking about the probability. All right, so that's oh, and there's a negative. I forgot about that. So we know this is Z. So if I take the first derivative of Z, just working this out a little bit at least, just the stuff that's apparent. So if I take the partial derivative of Z with respect to B, there's going to be the partial of B, the partial with respect to B of the sum in this. So technically that's going to be the partial derivative of each one of these things added together. So it's going to be the partial of B and e to the negative B E1 plus the partial of B e to the negative B or beta E2 plus, and that's going to continue. So this is going to be uh, negative E1 e to the negative beta e1 plus, I should say minus e2 e to the negative beta e2 minus, what do you think, Galva? That's good so far? I think that's all right so far. So if I was to combine this again into a summation, awesome, that would be negative sum of e I e negative beta e I. I mean, that seems reasonable. And why did I do this? Well, I did this for this reason. I got to get a second derivative of that as well, the bastards. So if I get a second derivative, b squared of z is going to be the partial derivative of this. That is going to be the partial of this. That's why I gave up math as a major, by the way. I was going to be a combined. So right now I'm getting 2 degrees. I'm getting a degree in physics, bachelor's degree in physics, and I'm getting a bachelor's degree in astronomy. I'm graduating this semester, which is why I got to make sure I pass all my classes. Not that I failed any classes yet, but it's still it'd be horrible if I fail one this semester and don't graduate. Okay, so I'm gonna graduate with a bachelor's in astronomy and a bachelor's in physics. But initially, before I added my double major, I was going to add math. So I was in my differential equations class, which is very relevant to physics, and I was considering majoring in math. And I was looking at the classes I was going to have to register for. Like, I was in class with a few math majors, and I was hearing from them and looking at the class schedules and all that stuff. And in that class, the professor threw in a few proofs as far as problems, and I was like, "Dude, I hate these proofs." And then when I looked into the math major, the next class I was going to have to take in the progression was a class of nothing but proofs. I was like, hell no. So I was like, I only reason why I wanted to do math as a major is because, as we can see, physics has a lot of math in it. But I quickly learned that I could learn all the physics I need to do for math pretty well without having to, you know, go into a strictly math class. And of course, as you can see, and as you reminded me on my exam, I do have to do some proofs, but it's not to the level that was. So I always thought astronomy was fun whenever I was able to take an elective class in science, because when you get like a physics degree, you have to take some kind of science elective, and you can pick from stuff like biology, geology, or something like that. I always did astronomy, so I decided to make my second degree astronomy. And Galba says, yeah, mathematics is all about proofs that you come directly from school. It's like a slap in the face, requires completely different thinking. I agree. So you feel my pain, Galba. You know what I'm talking about. And obviously you're familiar with this stuff because you're able to point out some of the algebra things there. So good on you for being up on some math and physics. But yes, I hate the strictly proof stuff. I like math, but I just like the kind of math that you do to solve the average physics problem. That's the kind of math I like. All right. So perhaps I'll finish this partial derivative, then I'll call it there. So let's see what this is looking like. I'll at least have the foundation set. And what I may do, because I don't want to keep y'all here all night when I'm trying to figure out this, whatever else they want us to do. But I guess this might really be it once I but I'm pretty sure this is not the proof, but we'll see. I mean, if after I finish this and I put a 1Z, pretty sure they want us to do some kind of manual thing on this side, not just do the right side. But I'll finish the right side. I'll probably stop there. So let's do one more partial derivative. Let's see what we end up with. So I have this equals, all right. So this will be similar to what I did before. This will be partial b of negative E1 E negative B. And I'm pretty sure there's a way to just do this and not break them apart like this, but I don't want to mess something up since I'm not so good with proofs in the first place. So this helps me just keep track of what I'm doing. So it's going to be the partial derivative of all that. So this is going to be negative E1. I'm going to have another E1 coming down. So this is going to be E1 squared, E negative B E1. So this is obviously going to be plus E2 squared E to the negative B E2. That should continue. So if I was to put this back into summation form, this would be the sum I of E I squared and E to the negative B E I. And now we have the second partial derivative of z with respect to beta squared. And what they're saying is that the expected value of the energy squared, I'll just have to divide this by the partition function and put that there. So they're saying that this equals 1 over z and times this summation. And actually, this is not so bad, I guess, because, yeah, this is not so bad, actually. Because if we look at this, we actually did this earlier. So this is the expected value squared, this part. We did that earlier. This is the probability. Oh, I see what they did. Okay, okay. So the probability, according to the uh, Boltzmann factor, like the probability of I, is going to be 1 divided by this is the partition function, times the Boltzmann factor. Okay, ain't that something? Because I have the moral support of Galva there, I was able to get through a proof, I think, right? This is from the equations in the book. So as we see, all we have to do is just uh, move this around a bit. 1 over z e negative b e I. So, and I'm pretty sure that is the expectation value squared right there. Because, oh, I gotta multiply the value. Yeah, I believe that's the ends up being the expectation value of that. Galva says, yeah, Matt. Yes, that was from earlier. Okay. So let's look at what we did here. Here I did the squared one. Let's say I'll add one more page from last problem. We have this. And this does in fact equal the sum I, the probability of I and EI squared from last problem. Thus, the equality is true. Right. Just sort of a shorthand because I'm not writing everything over again. But you agree, right, Galva? This is what we did earlier, and this is literally the same thing. It's just instead of doing a change in E, I'm just doing E word and taking the average of that. So yeah, I believe that does it. So all I really have to do is copy everything from last problem and not put the little square thing in front of it. And I think that's it. So I think I have this one. So awesome. It was good seeing you, Galva. Thanks for your tips, catching the typos. Thanks for your questions and comments. And I'll probably be back again. Thanks. Appreciate it. I'll probably be back tomorrow or Wednesday. So I don't know what I have going on tomorrow, but I'm trying to be more consistent on this channel because somebody had joined the Discord and let me know, hey, your video on linear algebra really helped. So I was like, okay, well, I'll be a bit more consistent here as well. Appreciate the best wishes, go over, and hopefully I'll see you again. I'll look for you next time. I would say expect me Wednesday. So I'll be back Wednesday evening. And I'll see what I'm working on there. I probably made some progression in the chapter, but I'll probably be like on chapter 6.6 or something. But I'll be on here on Wednesday. Thanks for the well wishes. Thanks for everybody who popped in. I'll see y'all next time.